will continue with this theme of remarkable geometric formulae, and this time we'll start with something which we shall call as the generalized cosine rule, and this itself is a little tedious to derive, and all I'm going to say is that it comes directly by a few algebraic manipulations of the cosine rule and as well as the sine rule. But the good news is that it is quite easy to remember. So I'm going to state the generalized cosine rule for the quadrilateral, and we will use notation which we have used before and we are pretty comfortable with, and let's call these as the diagonals d1 and d2. The generalized cosine rule says that d1 d2 whole square is equal to the opposite sides. Okay, so that's why it's easy to remember. The opposite sides, that is A and C, have to be clubbed together. So AC square plus BD square, which are the opposite sides, minus 2ABCD cos of B plus D, where B and D are opposite angles. So it doesn't matter, as you can see, which pair of opposite angles you use. You could also say A plus C. So this is the generalized cosine rule for the quadrilateral, and as before, slight manipulations of this formula, which is very easy to remember, please note that, is going to give us a series of extremely useful formulae. So let's start. The first one is what happens if this quadrilateral is cyclic. Well, we all know what's going to happen. B plus D is going to be 180, and cos of B plus D will then be -1, and one quickly sees that d1 d2 whole square is equal to AC plus BD whole square, and this implies that d1 d2 is equal to AC plus BD, and many of you will remember this or identify this as the famous Ptolemy formulae for the cyclic quadrilateral. So here it is. We have one nice formula coming directly from the use of this generalized cosine rule. But there is much more here. So now, first let me tell you what we are trying to derive, or what is the formula that we have on our radar, and it will come from a clever application of this formula and this diagram. So I'll keep these formula here, and now this diagram has to be slightly adjusted so to get a formula for a triangle. So I'm just going to draw the corresponding triangle with the so let's see, let me call this as, I'm just trying to draw the triangle here, so I'll just call this as A B C, and what we are hoping to do is get a formula for a Cevian which makes two parts of the opposite side, one of length m, another of length n, and the labeling goes as B, C, and this side will be called as A. This side will be called as A, and I just want to write this here up front because the algebraic manipulations will require you not to forget that m plus n is equal to A, and yeah. So can we get a formula, shall we call this as P, for the length of the Cevian AD, where it cuts the opposite side into two pieces, one of length m and the other of length n. And now you can see from the diagram that if you directly substitute into this formula, so d1 will be basically A, and oh, I forgot to mention that we're going to use, the clever use of this formula is let angle D tend to 180, nearly equal to 180 degrees, and that would mean that this quadrilateral will assume the shape of this triangle. So now we will substitute appropriately, and in the limit we are going to get the formula for P. So we have AP whole square is equal to B square n square plus C square m square minus 2BCMN cos of 180 plus A, and this simplifies to B square n square plus C square m square plus 2BC mn cos A. And now for 2BC cos A, we will use the cosine formula, and we'll get A square P square is equal to B square n square plus C square m square plus, and now I'm using the cosine formula, B square plus C square minus A square in the triangle MN. So let me make some space, since now we're done with this. This simplifies to A square P square is equal to B square n into m plus n, and now I want you to remember that m plus 1 is A, plus C square m into m plus n. Once again, remember that m plus n is A, minus A square mn, and finally, if you just cancel 1a here, 1a here, 1a here, 1a here, and 1a here, you get this famous formula, which is called Stevettes Formula, which will help you to calculate P. So AP square is equal to B square n plus C square m minus AMN, and please do relate it to this triangle, and you'll see that there is a nice amount of symmetry here. So what is the symmetry? B gets multiplied by B square gets multiplied by n, and C square gets multiplied by m, and then A gets multiplied by mn, and you will get A times P squared. So while this not very slightly daunting looking formula, but there is a symmetry here that will probably enable you to memorize it. So what I should try and do now is, we have still a little bit of work to do. So let's try to clean up our board, but we'll keep the triangle and we'll keep the Stevettes formula. Now, what we can do is slightly modified Stevettes formula to get the nice expression for a particular case. So one particular case we've already done, so I shall not repeat it. And for the length, when P is a median, and this implies that M is equal to N is equal to A by 2. So you substitute this here and you will get the formula for the length of the median, but we've already done it, so we shall not do that. But there are still two nice cases, and I shall presently do the first one. The first case is when this particular line, maybe I shall draw this again, when this particular line is a angle bisector. Okay, so let's do the case when this particular line is an angle bisector. So I'll just redraw this. So we're looking for the length of the CVN where that CVN happens to be the angle bisector. Okay, so for some reason the notation is IA, and then the rest of the notation is as we have done previously. So this is B and this is C, and this we've been calling it as M and N, and don't forget that M plus N is A. Now if you say that these two angles are equal, so let's call them alpha by 2 and alpha by 2, then we have an important relationship for the angle bisector, which is that B by C is equal to M by N. Now you use this along with this into this formula, and you will get the following formula, which is P squared is equal to BC minus MN. So I'll leave the simple algebraic manipulations to you, and I assure you that I've done it, and all you need to do is use this formula and this formula. Now this by itself is very interesting. It's one of the properties of the angle bisector that comes into play in many interesting problems. So we'll get back to this. In fact, I would like to do a quick proof of this towards the end of this video, but for now I just tell you that this is the formula where P is an angle bisector. Okay, now we should do one more small manipulation here. So there's another formula which okay, let me just tell that this P, let's call it equal to IA. There is another formula for the length of the angle bisector which may be useful and which is also looks very neat. And now all the symbols we've used here, B, C and alpha by 2 are clear from the diagram, divided by B plus C. Now all I'm going to say is that you can do the algebra and derive this. Just need to use the two ideas. One is that B by C is equal to M by N, and the other idea is the formula cos 2 theta is equal to 1 plus 2 cos square theta. So a little bit of trigonometry is all you will require to go from, please note that you it is better to proceed from here. So it is very important to proceed from here to here. Is not going to be difficult. So you have another formula for the length of the angle bisector. Right. So before, just let me take 2 more minutes and derive this very important formula. Now it's a very well known, very simple, but I think it's so important that it's worth spending 2 minutes and actually doing 2 proofs of this. So what is the theorem and what is it that we need to prove? I'll just do this. Okay, so we have a triangle. Okay, let me just use a white color. We have a triangle, and what we are claiming is that in this triangle, if you have an angle bisector, then the ratio of these 2 pieces, m is to n, will be the same as, okay, I'm going to change b and c. So b and c here will be equal to c by b. Okay, so let's do this. There are 2, I'll do 2 quick proofs. The first one is we shall drop a perpendicular, okay, from here and from here. Note that this perpendicular distances are going to be same. That is because this is a equal angle, and since the h are same, we can say that the ratio of the areas, so let's call this point D. So area of ADB divided by the area of ADC will be equal to half C into H divided by half B into H, because these H's are equal. So we have got 1/2 of this is equal to C by B. Now we will do this area ratios by a different method, and again as a standard idea. Both these triangles here have a common height h. If you take the height from h, okay, let's call it h star. So in this case, the ratio of the areas is going to be, the first area is going to be half m into h, and the other triangle is going to be half n. I haven't labeled it, n, half n into h stars. And once again, this happens to be m by n, and since both of them happen to be the ratio of these 2 areas, we get the nice that these 2 are equal. So m by n is equal to c by b. So this is very useful and often used in problem solving. But let's do the same proof in a slightly different way, because it's a standard construction. So we do have a triangle, and we have the angle bisector, and what we are claiming is that C by B is going to be equal to M by N. So the construction that is to draw a parallel line to AD passing through C. So that's the construction, and that constructed line is going to meet this line. Okay. So let's call it E. The main point is that EC is parallel to AD, and like I said, this is a very favorite construction. So what happens immediately is that this angle, which we've been calling it as alpha by 2, will be equal to this, which is equal to alpha by 2. But then, since it's angle bisector, this angle is also alpha by 2, and this angle will therefore be alpha by 2. And now we see very quickly that ACE is isosceles, and that's almost the end of the proof, or is it? So if it's isosceles, then AE is equal to AC is equal to B. So I shall write this as B. I shall write this as also B. And then finally we have triangle ABD is similar to triangle EBC because of the fact that two angles are same. So by AA, that is because of the fact that these two, because EC is parallel to AD. And finally what we have is, because of similarity, we have C by B is equal to M by N, and we are done. So the main reason why this standard proof was repeated is because of the fact that it's a standard construction, and of course we've used similarity. So with that, we end this session on remarkable form.